Okay, good morning. So welcome to the lecture 17. And today we will start a new topic. So today we will talk about rings and ring homomorphisms. Ring homomorphisms.
Will this be on the midterm?
Yes. So the midterm is cumulative. So basically everything that was on the midterm can be on the midterm. But again, but there will be even a homework assignment right before the midterm. That's so. Okay, so and let's start with the definition. So our definition one would be of a ring. So a ring and let's call it R is a triple of R with a pair of binary operations on R. So it is a set R equipped with two binary operations. Equipped with two binary operations which are called, okay, so plus and star, which are called addition and multiplications, which are called addition and multiplication. And satisfy the following list of properties. So the first property, called R1, is saying that R together with the binary operation plus is an abelian group. Abelian group. The second property, which is called R2, says that the binary operation star from R cross R to itself is associative. Associative. Let me move the drawing tablet slightly. And finally, the last property tells us about how these two binary operations interact with each other. So the property R3 says that for all A, B, C in R, the following two conditions hold. So first, if we take A and multiply it by B plus C, that's the same as A multiplied by B plus A multiplied by C. This is called the left distributive law. Left distributive law. Hello? And similarly, if we take a sum of A and B and multiply it by C, that's the same as if we take the result of multiplication AC and add the result of multiplication BC. And that's called the right distributive law. So the set together with two binary operations satisfying properties R1 to R3 is called a ring. Okay, so it is common to omit the multiplication sign, common to omit the star and write simply AB for A star B. Okay, so you might have noticed on this slide that we required separately in R3 we required separately the left distributive law and the right distributive law. And there is a good reason for that. So that will be our remark 1. Mark 1. So of course, when the binary operation star is commutative, well, then left distributive law implies right distributive law. Right distributive law, and of course vice versa, and vice versa. However, when the binary operation star is non-commutative, this is no longer true. So we have to require both distributive laws in the definitions. Laws in definition of a ring. So non-example for that will be in homework. Example will be in the homework assignment. Okay, so any questions so far about the definition? Now I assume that all of you are well familiar with the idea of the ring, and that's because the prototypical examples of a ring are rings of numbers. So prototypical examples. So first of all, if we look at the set of integers together with the binary operation plus and times, this is a ring, right? If we look at the set of rational numbers together with binary operation plus and time is a ring. Similarly, same thing goes for real numbers with two binary operation and for complex numbers. Okay, so this examples of sets with pairs of binary operations plus and times served as the kind of basic serves as a basic prototype of the definition we just introduced. Now, however, the kind of the main thing in the definition 1 is that we never actually require the binary operation star to be commutative. So there are examples of non-commutative rings, and let me start with the example you actually already seen. Example 1. And that'll be, if you look at the matrices, and by n matrices over the real numbers together with binary operation plus, which is addition of matrices, and binary operation times, which is multiplication of matrices. So n by n matrices with real entries is a ring. Well, you all know that the operation times is not commutative for n greater than 1. And of course, same goes for matrices. Same goes for matrices with integer entries, matrices with rational entries, and matrices with complex entries. So they also form a ring with the standard operations of matrix addition and multiplication. Now, there is an interesting kind of continuation of this example. So let's look at example 1a. In fact, let R be any ring, not necessarily commutative, not commutative. Well, then the set of n by n matrices with entries in R and binary operation plus and times is a ring. The only thing you should be careful when you define the matrix multiplication, of course, you kind of want to put all elements of the first matrix on the left and all elements of the second matrix on the right. And what you will get is a ring. Okay. Now, there is even more interesting example. And that'll be example 2. So let X be now any set. X be any set. And let R be any ring. Let R be any ring. Now, then the set of functions, which we will call as f calligraphic. So the elements of this function, the element of the set will be functions from X to the ring R. Is a ring. Is a ring where this addition and multiplication are defined as follows. So for all f, g in this calligraphic f, we can define f plus g. So that's a new function from X to R. And this function, when evaluated on element X small, is nothing as f evaluated on X small plus g evaluated on X small. And that's for all X small in X capital. And similarly, we will define multiplication of functions. So the result of the multiplication of two functions is a new function from X to R, which when evaluated on X is nothing as just the product of values of the functions f and g. That's for all x in x capital. Now here kind of, so this is multiplication in f capital, and this multiplication of course is assumed multiplication in a ring R. So in particular, integer valued functions on any set is a ring, real valued functions on any set is a ring, complex valued functions on any set is a ring, and matrix valued functions on any set is a ring. Okay. Now a slightly more elaborate example, which actually closely related with the previous one, is example 3. Example 3. So the set of all polynomials, the set of all polynomials in one variable with integer coefficients, is denoted as z square bracket x. So in one variable, let's say this is x. I apologize if you hear the music. That's from the neighboring building. I'm lecturing from the home this week, so that's I'm sorry for that kind of interruptions. Okay, so now this set of all polynomials, it is a ring. It is a ring. You can add two more polynomials by adding the coefficients in front of the corresponding power of x. You can multiply the two polynomials in the usual sense, and of course it will satisfy all kind of distributivity properties, etc. These two binary operations. Okay. And now let me go over another example of a ring. And this example is remarkable. So this will be a non-commutative ring. Non-commutative ring. Where all non-zero elements have multiplicative inverses. So we will talk a lot about multiplicative questions after the midterm 2, but it's still worth considering this example early. So this is non-commutative division ring. Example of non-commutative division ring. And this is the so-called quaternions, H. So H with a solid left line on the left, quaternions. Quaternions. So as a set, quaternions is just 4 tuples of real numbers. So as a set, this H is 4 tuples of reals. So they will be written in the following form. So likewise, complex numbers are 2 tuples of pairs of real numbers, which are written as a plus bi. Now we will have 4 real numbers, and we will write them as follows: as a plus bi plus cj plus d k. And again, so far this is just a way to write for real numbers, a, b, c, d, all reals. Now the addition is defined as usual. You just take a1, b1, I, c1, j, d1k, and you add them exactly as vectors in four-dimensional space. So if you have another quaternion, then the result of their addition is nothing as the quaternion with a1 plus a2 as the first component, b1 plus b2 as the second component, c1 plus c2 as the third component, and d1 plus d2 as a fourth component. Now the multiplication is actually much more elaborate, and you define it by the lengthy formula. Multiplication. So if we take a1 plus b1 I plus c1 j plus d1 k and multiply it by a1 plus b1 I plus by another one. a2 plus b2 I plus c2 j plus d2 k, then the result will be as follows. So for the first component, you will get a1 a2 minus b1 b2 minus c1 c2 minus d1 d2. Then for the second component, you will get a1 b2 plus b1 a2 minus c1 d2 minus plus c2 d1 times I. And finally, for the other two, you will get c1 a2 plus a1 c2 minus d1 b2 plus b1 d2 j, and similarly you get a1 d2 plus a2 d1 minus b1 c2 plus c1 b2 times k. Now the claim is that this h together with binary operation plus and star is a ring. Now R1 is immediate because with respect to addition, they behave as vectors in four-dimensional space. Of course, this is an abelian group, right? Need some calculations to verify R2, R3. Similar to how these calculations are done for the complex numbers. Of course, I'm not going to explain this on the blackboard. It's kind of too long, but believe me, it works. And one can actually think about them as follows. So if we take this I squared, this is the same as if you take j squared. This is the same as if you take k squared. This is minus 1. You can see it directly from the multiplication formula. And this is actually the same as I multiplied by j multiplied by k. So hence, if we look at the multiplication of I j, then we will get k. However, if we multiply them in a different order, J, I, we will get minus K. So from here, it follows that H is non-commutative ring. However, a remarkable fact about H, a remarkable fact is that every non-zero element is invertible, has multiplicative inverse. Multiplicative inverse. Okay, so to conclude, probably on this strange examples of rings, let me mention also the ring of differential operators. So this will be example 5. And here I won't go into any details. I'll just mention that if you look at the differential operators, and let's say that they act on, I don't know, infinitely differentiable functions of R for simplicity, but you can make this in slightly more general setup. So as a set, this will be the following expressions: P0 plus P1 and d by dx plus P2 d by d squared by dx squared plus P3 d cube by dx cube, etc. So here P0, these coefficients, let's say all the way to Pn, they belong to R C. They are just C infinity functions of R. Is a ring. I won't prove it, but you can multiply those. You can add them, and it will satisfy the distributive property, etc. Okay, so this basically concludes examples of rings. So any questions about examples? Okay, so let's talk about notations. So remark on standard notations. So let R with binary operation plus and times be a ring. Now, identity of an abelian group. Identity of an abelian group. Group R plus is denoted by 0. Denoted by 0. Moreover, we assume additive notation. Additive notation for this group, abelian group R. So as I said, it's R with a binary operation plus. In other words, the inverse inverse of A in R is denoted by minus A, denoted by minus A, and the nth power is denoted by NA. The nth power is denoted by NA. Oh, that's actually move it to the next slide. So this NA is nothing as A plus all the way A, and this is n times. When n is greater than 0, it's 0. When n equals than 0, and it's just minus A plus minus A plus minus A, absolute value of n times when n is less than 0. Now, the important thing here about this notation is that the above notation does not imply that that integers are elements of R. However, when this is indeed the case, we have some consistency. We have some consistency, which basically telling us that nth power of A is the same as n star A. For n belongs to Z, which is a subset of R in this case, and A belongs to R. Okay, so now there is a technical lemma. So basically, once we introduce the definition of a ring in the definition 1, we will have to prove that kind of standard properties of 0 of additive inverses hold. Lemma 1. Let R be any ring. R plus star be any ring. And 0 stands for the additive identity. 0 stands for the additive identity. Then we have the following. For all A, B, C, in R. Oh, sorry, for all A, B in R. First of all, we will get that A star 0 is the same as 0 star A is the same as 0. Second of all, we will get that A star minus B is the same as minus A star B and is the same as minus A star B. And finally, we will get that minus A star minus B is the same as, A star B. Note that in the lemma 1, we have never required this ring to be commutative. It can be any ring. Okay, so the proof it's written up in the textbook, but still let me comment on that, because it's kind of it's remarkable how we use the properties of ring. It's kind of interesting on its own. So let's prove the first part. Let's look at A star 0. So our goal is to prove that A star 0 is 0. And what we will do is we will take first A star 0 and add it with A star 0. Then by the distributive law, R3, that must be the same as A star 0 plus 0, right? Which, because 0 is an identity of an abelian group, is the same as A star 0. Now, what we have is that kind of this A star 0 plus A star 0 is the same as A star 0. But now we have that R plus is a abelian group. So by cancellation laws, for group R plus, we conclude that A star 0 must be equal to 0. Now, kind of the most interesting part of this proof is, of course, how we apply this kind of defining properties of a ring. Okay. Now for the second part, recall that minus x stands for the inverse, of x in a group R plus. Okay, and our goal to prove the standard property of multiplication. So let's look at the A multiplied by minus B. And again, let's what we can start with is the distributive property. So let's look at the following sum: A star minus B and A star B. Again, by the distributive property R3, this is the same as A star minus B plus B. And because R plus is an abelian group, then by R1, or by definition of minus B, if you'd like, this is the same as A star 0, which by the first part equals to 0. Well, so what we have is that then A star minus B is additive inverse inverse for A star B. And of course, the other thing is similar. Okay, so now finally let's look at the part 3. So let's look at minus A star minus B. To prove that it's the same as A star B, the only thing we need to do is to apply this second part twice. So first of all, it's the same as minus A star minus B, right? Then let's apply it again. The second case, and this is minus of minus of A star B. But now the R plus is an abelian group. So by the property R1, if we twice take the inverse in a group, then this is the same as A star B. Okay. So inverse of an inverse in a group R with a binary operation plus. Okay, so here we go. Now, similarly to how we defined subgroups, we can introduce subrings. Similarly to subgroups, one can introduce definition 2. So let R be a ring. Be a ring. We say that P is a subring of R, is a subring of R if the two things hold. So first of all, P is a subset of R, and P is a ring. And with respect, the same binary operations, of course. Now, examples of subrings would be as follows. So, example 6. If we look at the ring of integers, it is a subring of the ring of rational numbers, which is in turn a subring of the ring of real numbers, which is in turn a subring of the ring of complex numbers, which is in turn a subring of the ring of quaternions. So we can think of complex numbers as quaternions with zeros in the last two coefficients. So this is a chain of subrings. Okay. Now there is actually an even better example. Example 7. So let F denote the ring of functions. Let F calligraphic denote the ring of functions. Note the ring of functions. And here, for simplicity, we will just look at the functions, from reals to reals. So this is a set of functions from real numbers to real numbers. And Cn of R denote the ring of real valued functions, denote the set, well, it's actually the ring of n times differentiable functions. Well, functions. So what you would have is that inside of all functions, n times continuously differentiable functions, of course. Continuously differentiable functions. So what do we have? We have this f, right? Inside of f, there is a subring which consists, which is C0 of R, and this is continuous functions. So in the real analysis or calculus, you've learned that if you add two continuous functions, right, you get a continuous function. If you multiply two continuous functions, you get a continuous function. Now inside that, you have C1 of R. That's continuously differentiable functions. Continuously differentiable functions. Well, functions. Now this, of course, continues. So inside that you have C2 of R, etc. And actually, there is even smaller subring, which are infinitely differentiable functions. Functions which can be differentiated infinitely many times. And inside that, there's actually sits one example we already considered. Those are polynomials. So all polynomials are infinitely many times differentiable, right? Because the derivative of polynomial starting from some moment is just 0. So this is a chain of subrings. Chain of subrings. Okay. So any questions so far, by the way? This kind of material. More or less straightforward. Now, so we can define subrings similar to the subgroups, and of course we can define direct product of rings similarly to the direct product of groups. So let's introduce lemma/definition 3. So let R and P be rings. Let R, P be rings. Then the direct product which as a set, again, is just a collection of ordered pairs. Collection of ordered pairs R small and P small. R in R, P small and P capital, is a ring. A ring. With respect to the component-wise addition and multiplication. Component-wise and wise addition and multiplication. So this is what called the direct product of rings. Okay. Now, of course, like the study of groups is not so much the study of the groups themselves, it's rather the study of homomorphisms between different groups. Same goes with rings. So really what the most interesting part of the rings is not just how you add or multiply stuff in various examples, but it's rather what can we say about ring homomorphisms. So let's talk about ring homomorphisms. Ring homomorphisms and isomorphisms. Okay, so the basic idea of the homomorphism is a map which preserves the structure, right? So in this case, we have two binary operations. And we say that phi, function from R to R prime, is a ring homomorphism. Homomorphism. If it satisfies homomorphism property with respect to both binary operations. So if phi of A plus B is the same as phi of A plus phi of B, and phi of A star B is the same as phi of A star phi of B for all A, B in R. Okay, so if we have a ring homomorphism, we can define the kernel of a ring homomorphism. Let phi R to R prime be a ring homomorphism. Then the kernel of phi is precisely the collection of elements R small in R, such that phi of R is actually 0 in R prime. So this is the collection of all elements which are sent to additive identity. All elements which are sent to additive identity. Now, here the similarity with the groups continues, because in particular, this kernel phi is just coincides, in particular, or phi r plus to r prime plus is a homomorphism of abelian groups. Abelian groups, hence kernel phi coincides with the kernel of group homomorphism. Kernel of the above group homomorphism. Okay, so we would have lemma 1. So remember that kernel of a group homomorphism was a subgroup of the domain. Similarly, the kernel of a ring homomorphism is a subring of domain. So let phi from R to R prime be a ring homomorphism. Ring homomorphism. And then kernel of phi is a subring of R. Now, to prove this lemma, we basically have to prove that the kernel is closed under addition and multiplication. So this is very much similar to what we did with groups. So suppose A and B are elements of the kernel of this ring homomorphism. Then first of all, phi of A plus B is the same as phi of A plus phi of B, 0 plus 0, because both are in the kernel 0. And of course, the same thing works with their product. Let's look at phi of AB. This must be the same as phi of A, phi of B. And again, this is 0 times 0, 0. And that's again because these two are in the kernel, which means that phi of them is 0. Okay. Now there's an interesting, okay, so you might see that this is kind of straightforward. Now, with the kernel of a ring homomorphism, one can immediately associate the following neat example. I believe that'll be example 7. So remember that if X is any set, so let X be any set, and R be any ring, then the collection of functions f from X to R is a ring on its own. Is a ring. And let's look at the following homomorphism. Let's fix a point P in our domain X, in this common domain for all functions. Okay, so then we can define define phi sub p, and that will be a map from functions on X to R, which does the following thing. It takes function f in this f and sends it to the value of this function at the point P. And that's, of course, element in R. Now, the claim is that phi p is a ring homomorphism. Claim phi p is a ring homomorphism. Okay, so if we have a ring homomorphism, oh, and I should also say that, which is called evaluation homomorphism. Homomorphism. Now, once we have a homomorphism, we can look at its kernel. So then the kernel of this phi sub p is precisely the collection of all functions from X to R, such that the value of this function at the point P equals to 0. And this kernel is a subring of F. Okay, so if this R was just real numbers, so this was X, this was R, now here's the point P. Here's the point P. Then this subring would kind of contain all possible functions which are 0 at P. Okay. So any questions about this example 7? Now, similarly to the group theory, we had the trivial group. So with rings, we will have the 0 ring. So example 8, 0 ring. So as a set, it just contains a single element, which is additive inverse. And if we add it with itself, it's 0. If we multiply it with itself, it's 0. Now the property R3 is satisfied because if you take 0 plus 0 and multiply it by 0, that's the same as 0 times 0 plus 0 times 0, 0 plus 0, 0. Now, lemma, let R be any ring, and then psi from R to 0 ring is a ring homomorphism. Okay, kind of silly example, but still, to see the analogy with a trivial group. Okay, so the last part, let me introduce definition 2. Definition 2. So we say that phi from R to R prime is a ring isomorphism, ring is a ring isomorphism if, first of all, phi is bijective, and second of all, phi is a ring homomorphism. So that's kind of obviously we would kind of have the statement that all collection of rings is partitioned into equivalence classes up to isomorphism. So if R is isomorphic to R prime and R prime is isomorphic to R double prime, then of course R is isomorphic to R double prime. So we can talk about isomorphism classes of rings. Okay, so more facts on ring homomorphism. And that's complete analogy. With group homomorphisms. Okay. F R1 to R2 and G from R2 to R3 are ring homomorphisms. And G from R2 to R3 are ring homomorphisms. And then so is G composed with F, which is a function from R1 to R3. If I from R1, well, let's say from R to R prime is an injective ring homomorphism, then I of R is an isomorphic ring to R. Okay. So any questions so far? So this this was more or less identical to groups, and that's not a coincidence. In fact, because both groups and rings, the collection of all groups and rings, they share certain properties, and particular, these are the so-called additive categories, but we won't talk about this in this course. Now let me see if I want to go to multiplicative questions this time. So we have like 10 minutes left. So probably, let me say, in the remaining time, probably let me make some remarks on different notations throughout the literature. So that will be definition 4. Let R be a ring. Let R be a ring. Now we say that R is commutative ring, is commutative ring if the multiplication is commutative. If AB equals BA for all AB in R. For all AB in R. And we say that R is a ring with unity. A ring with unity. If there exists an element, if there exists an element which we denote as 1 in R, such that 1 times A is the same as A times 1 is A. For all A in the ring R. Now, here's the interesting thing. For example, zero ring is a ring with unity. Because there exists this element 0 such that a kind of 0 times 0 equals 0. But here's an important thing. Now, in the literature, there exists a discrepancy in the definition of a ring. Remark. There exists a discrepancy. Just discrepancy. Throughout the literature. The literature in the definition of a ring. And some authors refer to rings with unity simply as rings. Important thing here, in our convention, which is used in the textbook and which will be used on lectures throughout the course, not every ring has have a unity. Have a unity. And let's look at example to which we will return at some point. Let's look at the set of even integers. 2z. The set of even integers is closed under addition and multiplication. Hence forms a subring. Forms a subring of z. But there exists no there exists no a and 2 times z such that a times b is the same as b times a is the same as b for all b and 2z. So 2z is not a unital ring. 2z is not a unital ring. At the same time, in the textbook, which requires all rings to be unital, in their convention, 2z wouldn't be a ring. So this is important to keep in mind when you will look for external resources, different textbooks, and so on, that some authors consider only rings with unity. This makes some technical problems, so later when we will study, I can elaborate why actually I think this is better idea to consider all possible rings, not just rings with unity. So later when we will study the so-called ideals, so that's ideals will be for us, the ideals will be a subgroups, will be a subrings, and they will play the role similar to the role played by normal subgroups in group theory. Now, the authors which require all rings to be unital would have to won't be able to say that ideal is a ring. So it brings some technicalities to the proof and overcomplicates it in some way. So that's why the textbook consider all possible rings, not necessarily unital, and we will stick to that convention in the lectures. Okay, so that's a good place to stop, and I hope you all have a good spring break. I will post some announcements about the exact format of the midterm 2 sometime later this week. Sorry, that's kind of a lot of changes happening quickly, and I will also hold office hours according to the usual schedule next week. So if you would want to join the office hours, just join the meeting with the same meeting ID during the standard time, and I'll be there to answer all possible questions about the homework or the material covered so far. Now, if you have any questions, please feel free to unmute and ask them.
So in a ring, we only require that R and plus together make a group. We don't require that R and star make a group.
Yes, we don't require that, and in most of the cases, this is not true. So, for example, if we look at the examples of a ring, at the prototypical examples of a ring, right? None of that really form a group with respect to an operation star. And the problem is, in all of them, 0, which is the additive identity, will not be invertible. Actually, the only case when it is invertible is when you consider a 0 ring. Does it clarify the question?
Yeah, so then when we're looking at a unital group.
Unital ring.
Oh, sorry, a unital ring. That does also, it just requires that there exists an element in the set itself, which could be kind of like the identity of a group.
That's right. But here's good point. Very good point. Thank you. So in the unital ring, we require to exist the unit, but we never require that every element has multiplicative inverse.
Okay.
And unless this unit actually coincides with 0, like in the example on the bottom of the slide of the 0 ring, this would never happen, that kind of every element is invertible.
Mm-hmm.
And that's precisely what we will talk about next time after the midterm 2. So we will talk about the multiplicative questions. So what really happens with multiplicative inverses for elements in a ring. And it turns out to be quite interesting. In particular, with every ring, you can associate the so-called ring of units, the group of units. So that will be a subset for which all elements have multiplicative inverses. So that's an excellent question, and it kind of it's in a sense an introduction to what will happen next. Thanks. Any more questions? Okay, so then I'll stop the session and I will return. So I will save the video for the lecture and I will return in a few minutes with office hours with the same meeting ID. Thank you.